These are notes for Mel Ham's Math 70, Monday, April the 6th, section 7.6, page 424. This is the last section in chapter 7, which will be covered on the exam. You're having an exam this coming Friday, which is April the 10th, covering chapter 7. One thing I'm adding is to skip problem number 2. We're not going to do problem number 2. The original homework was 1 through 26. We're skipping problem number 2. Problem number 1, you're given this triangle. Again, I'm making quick and dirty triangles. I didn't get a ruler or make them look nice, but just to get the idea. So they give us a triangle which looks like this. Capital A, B, and C are points. The points of the triangle. They're sometimes called vertices or vertex. One vertex, two vertices. And then the sides are little a, b, and c. Notice the convention that capital A, this vertex is opposite side A. Capital B is opposite side B. Capital C is opposite side C. That's considered standard notation for triangles. Then we have the definition of the sine of an angle, SIN, for three-letter abbreviation. Sine of A is defined to be the opposite side over the hypotenuse. So from angle A, the opposite side is little a. The hypotenuse, the longest side of a triangle, is little c. So we have little a over c. The cosine of angle A, the three-letter abbreviation for cosine is COS. That's defined to be the adjacent side divided by the hypotenuse. So the adjacent side to angle A is B. In case you're wondering, can't C also be considered the adjacent side? Well, C is already the hypotenuse. So the adjacent side is never the hypotenuse. It's the side that's next to A but is not the hypotenuse. So in that case, that would be little b. And the hypotenuse we already know is little c. The hypotenuse is always the longest side, and the hypotenuse is always situated opposite the right angle in a right triangle. Then we have the tangent of A. The three-letter abbreviation for tangent is TAN. Tangent of A is defined to be the opposite side divided by the adjacent side. So opposite angle A is little a, and adjacent to angle A is little b. So the answer would be little a over b. For 4, 6, and 8, they give us two sides of the triangle. We have to find the third. I've labeled the side that they didn't give us as x in each instance. In the textbook, they did not give us the x, but we have to go ahead and find it. Sometimes it's the hypotenuse, like here, and sometimes it is not. So we have to figure it out. So we use our Pythagorean theorem to find x. That looks like the hypotenuse. So I use my a squared plus b squared equals c squared. 8 squared plus 15 squared is equal to x squared. Solve for x. 8 squared is 64. 15 squared is 225 equals x squared. Add them up, you get 289. Take the square root of 289 and you get 17. So the hypotenuse is 17. Then I use the definitions of sine, cosine, and tangent. So the sine of theta, this angle is called theta, T-H-E-T-A. It's one of the Greek letters. It's often used in geometry and trigonometry for angles. So if you put a 0 and a little line across it, that's called theta, T-H-E-T-A. Sine of theta is defined to be the opposite over the hypotenuse. So opposite theta is 15, and the hypotenuse is 17. So 15 over 17. Cosine of theta is defined to be the adjacent over the hypotenuse. So adjacent to theta is 8. Once again, this other side is not considered the adjacent because it already has a name, that name being the hypotenuse. So the adjacent side is the one that is not the hypotenuse. And the adjacent was 8, and the hypotenuse we found was 17. Finally, the tangent of theta is defined to be the opposite divided by the adjacent. So from theta, opposite is 15, adjacent is 8, so 15 over 8. Problem 6, similar, they give us the 20 and the 29. We have to figure out side x, I'll call it. 29 being the hypotenuse, so a squared plus b squared equals c squared. X squared plus 20 squared equals 29 squared. 20 squared is 400. 29 squared is 841. You can punch these in your calculator, of course. Subtract 400 on both sides. X squared equals 441. Take the square root. X is equal to 21. So this side here is 21. So relative to angle theta, the sine of theta, again, is defined to be the opposite divided by the hypotenuse, so the opposite side is 20. The hypotenuse is 29, so we have 20 over 29. The cosine of theta is defined to be the adjacent divided by the hypotenuse, so the adjacent, we found that out to be 21, and the hypotenuse is still 29. And the tangent of theta is defined to be the opposite over the adjacent, so the opposite side is 20, the adjacent side is 21, so 20 over 21. Problem 8, they give us a picture like this. So 3 and 9, and we have to find the hypotenuse again, x. So using the Pythagorean theorem, x squared is equal to 3 squared plus 9 squared. 3 squared is 9, 9 squared is 81. Add them up, you get 90. X is equal to the square root of 90. A little bit of work that you might recall from algebra. I can take out a perfect square, 9. 90 is equal to 9 times 10. And the square root of 9 will come outside and change to 3. So x is equal to 3 radical 10, or 3 times the square root of 10. I will often just say radical 10, which means the same thing as the square root of 10, but it's a little bit easier to say radical 10 than the square root of 10. So I just go back to the definitions that I had over here. The sine of theta is the opposite over the hypotenuse. So relative to theta, the opposite is 9. The hypotenuse is 3 radical 10. 9 divided by 3 is 3, so 3 over radical 10. And for me, you may leave your answer as 3 over radical 10. Sometimes you've heard of rationalizing a denominator. I'm going to forgo that. You don't have to rationalize a denominator. Although if you know how to rationalize a denominator and you do it correctly, I'll still accept it. But for now, we're just interested in getting the quick trig function. So 3 over radical 10 is fine. Cosine of theta is the adjacent over the hypotenuse, way back over here. So the adjacent side of theta is 3. And the hypotenuse we found was 3 radical 10, cancel the 3, so 1 over radical 10. And the tangent of theta is defined to be the opposite over the adjacent, so the opposite is 9, the adjacent is 3, 9 over 3 is 3. Problem 10 over here, something similar. You're given theta, 60, 80, and x, the hypotenuse being 80. So x squared plus 60 squared is equal to 80 squared. 60 squared is 3600. 80 squared is 6400. Subtract 3600, you get 2800. Take the square root. X is the square root of 2800. A perfect square that goes into 2800 is 400. So 400 times 7. Square root of 400 will come outside and change to 20. So 20 radical 7. And once again, I use my rules for sine, cosine, and tangent. Sine of theta is defined to be the opposite over the hypotenuse. So that would be 60 over 80. That reduces to 3/4. Cosine of theta is adjacent over hypotenuse. So the adjacent side is x here. Again, it's not 80 because 80 is already called the hypotenuse. So remember, the adjacent side is the side next to theta, but it's not the hypotenuse. So we found that to be 20 radical 7 divided by the hypotenuse of 80. And 20 and 80 cancels, leaving me with a 4 on the bottom. So radical 7 over 4. Again, radical means root or square root of 7 over 4. The tangent of theta is defined to be the opposite over the adjacent, way back over here. So the opposite side is 60. The adjacent is 20 radical 7. 60 divided by 20 is 3, so 3 over radical 7. Then we just have some problems in punching out the calculators. These are very easy once you know what to do. So you need to get a calculator, a scientific calculator that has sine, cosine, and tangent. So on my particular calculator, and maybe you've got something similar if you have a TI, the calculator looks like this, and we have a sine, cosine, and tangent button, sine, cosine, tangent, which lets you just punch these out. One thing to watch out for is on most calculators you can have either degree mode or something called radian mode, and some even have something called gradient. You have to be in degree mode. We're doing all of these in degrees. So there's a way to change the mode on your calculator. You have to check your own calculator for mode. On my calculator there's a button called mode. So just check your own calculator. You have to make sure that you're in degree mode. If you're in something called radians, which we're not going to get into, or something called gradients, then you don't want that. So push the mode, change the mode so that you're in degree mode. If you're not sure how to do that, you can send me an email, maybe a picture, photo of your calculator, and I can help you with that. In addition, one other thing that I noticed you can do is just if you go to Google on your computer or even on your cell phone, and you can just type these things directly out as long as you put degrees. So I tried this on my computer and even cell phone. If you, for instance, type sine, S-I-N 62, but you have to put degrees, because if you don't put degrees, the automatic thing that the computer would do is make it in something called radians, and you don't want that. So if you type sine 62 and then literally type degrees, D-E-G-R-E-E-S, it'll give you 0.8829. So on my calculator, I just hit sine and then type the number 62 and hit enter. It gives me 0.8829. Now some calculators, you actually have to go backwards, and what I mean by that is you have to hit the 62 first and then hit sine. So I would just say experiment with your calculator. There's only two possible options that I've seen. You either hit sine 62. If that doesn't work, then go backwards, hit 62 and sine. And once again, you have to be sure that you're in something called degree mode, not radian mode. Okay, so sine of 62 degrees was 0.8829. The directions in the homework, it says round to the nearest 10,000ths, or 4 digits to the right of decimal point. Then do the same thing with cosine. So hit the cosine button. So on my calculator, cosine is over here. So I just hit cosine 11. Some of you hit 11 and then cosine and then 0.9816. Again, worst comes to worst, you don't have a scientific calculator. You can just type this literally on your computer or cell phone, and let's say if you're in Google, then just type cosine 11 degrees. You have to write D-E-G-R-E-E-S, because if you don't, it'll give you something in radians, which you don't want. And so I get 0.9816. And you can see all the other ones here. Cosine of 21.9 degrees, 0.9278. So you can check your answers with mine. Tangent of 63.4 degrees. So tangent button, T-A-N, is right over here. So hit tangent 63.4. Again, make sure you're in degrees. For some of your calculators, hit it backwards, hit 63.4 tangent. Just experiment with your calculator until you get the answers that I'm getting, 1.9970. Tangent 35.1 degrees, I get 0.7028. And the sine of 50 degrees is 0.7660. So this is all we have to worry about in terms of trig. Now, incidentally mentioned, there are 3 other trig functions, but we're not going to go over them. They're basically reciprocals of sine, cosine, and tangent. They are the cosecant, secant, and cotangent. Don't worry about them. I'm not testing you on those. If you take a formal trig class, trigonometry class, then you'll get all of those there. All right, so these are notes for Math 70, Monday, April the 6th, 7.6. And this is the last section of Chapter 7, and you're responsible for all of Chapter 7 for the exam on Friday, April the 10th. Once again, some reminders. Yes, I realize I'm going fast, but because this is a video, you can always fast forward or rewind as often as you wish. If this is too small, you can't read it. Remember that I've always attached this actual notes, and it scans, so it should be better than what you got from me before the spring break. So ideally, you have this paper full size in front of you, so you can just follow along with me as I point to certain things. It's probably easier to look in your paper and just listen to the audio compared to trying to follow along with what I have here. And as I point out certain things, you just look on your full size paper, hopefully, for what you have.